Hi all, welcome to part 3, talking about water and water's properties that allow it to facilitate, as it says here, a suitable environment for life based on its attraction to itself and other things that are polar. All right, and so we're going to talk a bit about water's ability to moderate temperature. We should start with a definition of what temperature is. Okay, and in order to describe temperature, we have to define what kinetic energy is. So kinetic energy is the energy of motion, and this is different than, let's say, potential energy, which is energy based on position or location, as mentioned before. So the kinetic energy that's associated with random motion of atoms and molecules, and all atoms are in random motion. They're rotating, they're moving, they're vibrating. So the kinetic energy that's associated with random motion is called thermal energy. Okay, so temperature, it represents the average kinetic energy, energy of motion, of the molecules in a body of matter. Okay, so it represents the average kinetic energy of the molecules in a body of matter. And we define heat as thermal energy in transfer from one body of matter to another. Okay, so temperature, the average kinetic energy of molecules in a body of matter. So water is able to moderate temperature, right? And what that means is that it's capable of absorbing heat from warmer air. And so it cools that warmer air, and it can release stored heat to cooler air. So it keeps the temperatures within a more limited range than they would otherwise be. Because of its properties, and you're probably going to guess what it is, and you're going to be right if you guess hydrogen bonding. All right, so hydrogen bonding between the water molecules is going to allow water to absorb, right, or release a large amount of heat without changing its own temperature, which, remember, is the average kinetic energy of the molecules or atoms in a body of matter, right? So the having to break these bonds, right, is going to allow, before molecules can speed up and start moving faster and faster and faster, allows it to absorb a tremendous amount without changing its own temperature very much. Okay, and then they show you how coastal areas have more moderate climates often than areas that are not coastal. And you can take a look at the difference between, let's say, Palm Springs and, well, it's not so perfect because there's not one right here. How about we do Los Angeles and Riverside, because we can move laterally that way, right? Very different in temperature, a very big difference in temperature based on position, right? Los Angeles on the water, so it stays within a fairly limited range of temperatures based on the effects of the water being able to absorb heat when it gets hot and release heat when it gets cold. Okay, so water has what we call a high specific heat. So let's define what specific heat is. Here it is. Specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree centigrade. So you're looking at the specific heat of water is 1 calorie, right, for every gram, for every degree centigrade. And if you want to know how to define a calorie, I put it at the bottom, okay? And also, your book lets you know that the calories that we talk about now are not the same calories as are on like food packages. So just read below, not sure. Okay, so water is said to have a very high specific heat. I haven't shown you a chart yet. I will in the next slide. But that specific heat is high because in order for any kind of heat, right, in order for 1 gram of the substance to actually change its temperature, many, many, many hydrogen bonds have to be broken in order for it to change its temperature by 1 degree up, right? So water resists changing its temperature because it has high specific heat, and the high specific heat is traced to the fact that the water molecules are hydrogen bonding with one another, right? So you don't get a temperature change, an increase in the average kinetic energy of the water molecules for quite a while after heat is actually applied, because you have to break all the hydrogen bonds between the water molecules first. So take a look. Here's specific heats of some common substances, 25 degrees centigrade. Okay, so let's take a look. This is what we have here. I pointed out aluminum and stainless steel and water because I wanted to make the case, and your book says the same, that you can actually burn yourself on a pot. Like we have aluminum pots and stainless steel pots. You can actually, if you were to put your finger in water, in the pot, you're trying to heat up water, let's say the water might be lukewarm, but if you then went to move the pot by its handle or touch the outside of the pot, figuring that it was not going to be hot because the water inside hadn't even heated up yet, you would be probably very sadly mistaken because you could burn yourself. Because look at the specific heat of stainless steel and the specific heat of aluminum, way below the specific heat of liquid water, right? So this is what we've been saying. When a source of energy strikes it, the hydrogen bonds, H bonds, that's what you see here, must be broken before the heat can be transferred and all those water molecules begin moving faster, right? It's not the same. It's one of the highest specific heats of any liquid known. Okay, so it's very high. Just look at all of the different things that are listed there. Okay, so specific heat measures the amount of heat energy needed to raise the temperature of 1 gram of a substance by 1 degree centigrade. Fine. Water has a particularly high specific heat. Just look at all these, which means that more heat must be added to the water than to most other substances to raise its temperature, right? And this is based, once again, on hydrogen bonding. All of those hydrogen bonding between all of the different molecules of water, right? You've got to break those in order for them to really start moving at a faster clip. Okay, now water can actually also moderate its own temperature, right? And organisms do this as well by something called evaporative cooling. All right, so let's take a look. So evaporation, vaporization, I'm sure you know this, it's a transfer of a substance from a liquid to a gas. The heat of vaporization is the heat a liquid must absorb for 1 gram of it to be converted to gas. That makes sense, right? So how much heat has to be absorbed by a liquid to be converted to a gas? Once again, you can think about, would you think water has a high heat of vaporization, right? It probably does. If we were to put milk on the stove and watch it, the same amount of milk as water, the milk would boil faster than the water would boil once again because you're dealing with the water molecules hydrogen bonding to one another. But anyway, evaporative cooling is as the liquid evaporates. So as water molecules go from liquid into gas, then the liquid surface that's left behind cools. And this is a process called evaporative cooling. It's the same reason why human beings sweat. Right? We put water on, we sweat water, or some water and ion mixture, and then when it is pulled up into vapor, the surface that is left behind is cooler because it pulls, right, it requires heat to move from a liquid into a gas. So it pulls heat from the skin. This is why on a humid day when it's very difficult or more difficult for water to evaporate from the surface, we're much more uncomfortable because we've lost our ability to moderate our temperature as easily as we do because the air is not as dry as we need it to be to have evaporation of the sweat occur and the cooling that occurs as a result. It's also, I mentioned to you transpiration in plants and talked to you about how plants, the water leaves the plants as water vapor, and that actually also has a cooling effect. So even though water vapor leaving the plant has the ability to dehydrate the plant and puts the plant in danger, when transpiration is occurring, so water is leaving the plant as gas, it actually cools the plant. So that is one of the benefits of transpiration for plants. Okay, but this evaporative cooling of water where the change from liquid to gas stabilizes temperatures, right, in organisms and also in the body of water, because once those water molecules with much more kinetic energy leave, what's left behind are water molecules that have lower kinetic energy. Okay, so we sort of get to our fourth. We've talked about the cohesive behavior, the fact that there's expansion upon freezing of liquid water into solid ice, the ability to moderate temperature, hydrogen bonding at the center of all of these, and now versatility as a solvent. So let's take a look. This is once again going to be based on water's polarity. water's ability to interact with others, things that are polar, okay? Likes to interact with like. So polar things like to be with other polar molecules, as we will see. Okay, but first we have to define or remind one another of what a solvent and a solute is. Okay, so water can be called the solvent of life. Right? A solution is a liquid that is completely homogeneous mixture of substances. That's what we refer to as a solution. In a solution, the solvent is the dissolving agent, right? So an aqueous solution is one in which water is the solvent, right? And that is what we refer to as like the cytoplasm. Our cytosol is an aqueous solution because water is the solvent. And the solutes are the substances that are dissolved in the solvent. So in all of our bodies, we have aqueous solutions based on water being our solvent and many different things being dissolved in it. Many different solutes are dissolved in our solvent, which is the aqueous solution. But let's just look at a beaker with some water. So we have some pure water, and when we drop a salt, an ionic compound, and we remember how that compound was made, right, through the electron transfer, right, sodium giving up one of its electrons to chlorine, right, and then both ionizing, sodium becoming a cation, chloride becoming an anion. That's what you've got there, and then they attract one another through strong hydrogen bonds. Strong ionic bonds, strong when it's dry. But you drop that salt that's being held together by ionic bonds into water, and what happens is the water forms spheres sort of around each of the ions, and they're called hydration shells, right? So each ion is sort of teased apart from the others, and then the water molecules arrange themselves in a way where positive is attracted to negative, partially positive, okay, attracted to fully negative here, but you have an electrostatic attraction there. So it's saying water is this versatile solvent due to its polarity. So I just took this out here and showed you this because it reminds you of the partial charges on the oxygen. So each one of these white little shapes, this is the oxygen molecule. Here are the two hydrogen molecules that are involved in polar covalent bonds with the oxygen, right? Since there is less electronegativity on the hydrogen atom than there is on the oxygen. Remember, the electrons of the bond, of the covalent bond, pull up towards the oxygen, right? And the same with this hydrogen's, the electrons it's sharing with that same oxygen atom pull up and spend more time around the oxygen. So it gives that oxygen a partial negative charge, and it leaves the hydrogens partially unshielded, so they have a partial positive charge, and now these water molecules will orient themselves in an orientation around the chloride ion so that it puts its partially positive hydrogens, right, towards this negative chloride, right? Positive attracts negative, that's what you have here. Then if we look at the sodium atom will be surrounded by water molecules, but not the hydrogen part of the water molecules. The oxygen orients itself so that it is closer to the sodium ion, the cation, and not the hydrogen atoms, right, of each water molecule, because those are partially positively charged, and partial positive charge doesn't like to interact with positive charge, right? Opposites attract electrostatically. So with polarity, like dissolves like, but with electrostatic interaction plus attracts a minus. So that's it. When an ionic compound is dissolved in water, each of its ions gets surrounded. So they're teased out and teased apart. And so salts dissolve in water, and this little block of salt breaks up as the water molecules orient themselves to put their sort of best foot forward, right? To put the appropriate atom of the water molecule facing the ion that they like to interact with. Okay, but then are you thinking, okay, water can only dissolve or interact with ionic compounds? And the answer is no. Water can interact with molecules that are not ionic, that are actually just polar, right? And that's perfectly fine. And what we see here is a large molecule, maybe it's a protein or something like this. And so water molecules come on up and they can make hydrogen bonds, right? So this would be perhaps an oxygen, or this could be a nitrogen here. I'm just taking that dotted line to mean hydrogen bond, right? And this is the oxygen of a water molecule here. So this is partially positive something, so this could easily be hydrogen that is polar covalently bound to an electronegative element. And so you get a hydrogen bond going, right, in these circumstances. So it doesn't have to be that something has to be charged in order to have a nice interaction with water. It just has to be polar. So we have to define something, and we'll define something that has an affinity for water as a hydrophilic substance. So hydro meaning water, philic and affinity for or loving. So this is a water-loving substance, right? Is anything that has an affinity for water, and a water-loving substance is going to be a polar substance, a substance that has regions that are more positive and regions that are more negative, right? Or it could be an ion of one charge or the other, right? All of those things will have a very nice time interacting with water, because water can orient itself to accommodate interaction with either positive or negative, or partially positive and partially negative. So this is a lot of versatility water has as a solvent, because so many things are polar. So it likes to interact with these things. Okay, but what about things that aren't polar? So now we have to define hydrophobic. So this is something that is water fearing or water hating. A hydrophobic substance is one that does not have an affinity for water. Right now, have we met a hydrophobic substance? Well, in chemistry, yes, right? Because we looked at bonds that are covalent, not polar covalent, but covalent, so much more equal sharing of electrons. In this diagram, they've shown carbon and hydrogen, right? And this arrow is pointing to the carbon to hydrogen covalent bond, and it is labeled as a non-polar bond. And that is because the electronegativities of the carbon atom and the hydrogen atom are close enough for the electrons to be more or less shared equally between these participating atoms. Right, so it doesn't give an overall partial positive to either one of these atoms, or partial negative. So this is what we refer to as a non-polar covalent bond between the carbon and the hydrogen, right? And so when you drop something that has non-polar covalent bonds in the middle of water, what you wind up doing is you wind up messing up the hydrogen bonding network that's going on. And if you think about the little video that we saw at the end of part 2, with the water molecules twisting and turning and making all those different hydrogen bonds with one another, changing all the time, but still in an incredible amount of interaction between them, you pop in some things that do not like water, right? They are hydrophobic substances, and they disrupt the hydrogen bonding network. So what winds up happening is that sort of the water molecules tend to push these water-loving elements together so that it can maximize hydrogen bonding between the water molecules around it. So you sort of shove it all into the same place. And maybe this is not such a good analogy, but if you think about having, dust bunnies all over the place in your house, and you're stepping over them, and you're trying to, let's say you have socks. I'm going to change the analogy. Here we go. You have socks, you're wearing fuzzy socks, you're walking around your apartment, and you keep bumping into these dust bunnies, which you then pick up from your fuzzy socks. So it's much easier for you to be able to avoid the dust bunnies if you were to sweep them all together and put them in one area. Haha, it's not the worst analogy I've ever given. I've certainly given way worse analogies than that. So you're minimizing the disruption on your walking pattern, on your gait all around your apartment if you stuff them all, those dust bunnies, in the same place, push them off to the side. So that's kind of what water molecules are doing, is shoving together these water-fearing or water-hating elements so that they can maximize the hydrogen bonding that's going around them, right? And not have to deal with each individual disruption by having them separated. And it's the reason that oil, oh, I'm sorry, I'm so loud. It's the reason that oil collects, right? If you drop oil into a glass of water, and maybe you should try this, live a little, do this at home if you've never seen it, you'll see that the oil sort of comes together. It's the way that it is easier to clean up an oil spill from a tanker, for instance, because the oil starts to coalesce. So these kinds of pushing together are often called hydrophobic bonds or hydrophobic forces. But it's a little bit of a misnaming of it, because it's not that this nonpolar hydrophobic hydrocarbon over here that I'm circling with my cursor has an attraction for that one, which you might think would be like the bond or the force. It's that the water shoves them together, right? The coming together is because water is repelling them, right, and pushing them together. And then, right, so it's not an attraction of one for the other that causes them to come together. They're shoved together. But then when they are together, they can attract one another by van der Waals, right, with the temporary fluctuations in the electron clouds around these atoms can cause a brief change, in polarity, partial negative for just a second, and this hydrogen atom might be partial positive because the electrons it shares with this carbon are up that way. And so once they are together, they can have van der Waals attractions or van der Waals forces, but that's not how they get together. They get together because it is disruptive energetically for the hydrogen bonding network of water to have these nonpolar molecules inserted. So they put them all in a group. Okay, so I will stop here and I will see you for part 4.